In lesson 6.1, we're going to solve systems of equations by three processes: graphing, substitution, and elimination. This is a concept that you learned in Algebra 1. And in Algebra 2, we're going to take it and we're going to expand it. Instead of doing just lines like Algebra 1, we're going to eventually do lines and parabolas, quadratics, or parabolas and parabolas, quadratics and quadratics. So, getting started, let's refresh some Algebra 1 skills that you haven't seen in a while. To begin, a system of equations is two or more equations. For now, we're going to be talking about two, but in a few lessons, we're going to actually branch that out to three different equations. More on that to come. The solution of a system is often called the point of intersection, or POI for short. When we say POI, point of intersection, we literally mean point as in an ordered pair. And it happens to be the point or the ordered pair where each of the lines intersect, each of the equations intersect. So in this case, they're lines because they're both linear graphs. Now, there are three types when you're talking about solving a system of linear equations, so also known as a linear system. If you have a blue line, seen here, obviously not drawn very well, and then you have a red line, this is a system because it only takes two equations to become a system. The answer, the solution, would be this point of intersection right where they cross, the x comma the y, the point of intersection POI. So this is an example of where there's only one solution because you only have one point of intersection where blue and red made purple. Now, if you have the same line, blue, and then you graph your second equation, and it ends up graphing entirely the exact same way to where one line is actually on top of the other. Well, blue and red make purple. So that's what's happening here. That's what that purple line is signifying. There are actually an infinite amount of solutions because there are an infinite amount of points on that line where the two graphs intersect, where the two graphs touch. So we're going to call this, it's going to be really, really tight, infinitely many solutions, or IMS for short, because there are literally an infinite amount of solutions. Okay, so what happens if you have a system, aka two or more equations, in this case two lines, and they don't intersect? So blue and red are graphed, and there is no intersection point, no POI. Well, if there's no intersection point, then there's no solution. No solution in algebra has a symbol. It's like a circle or a zero with a slash through it. That's one way to show no solution, or you can just write no solution. That's fine too. So let's talk now about the three ways of getting either one solution, infinitely many, or no solution. The first method that we're going to teach today and talk about is just simply by graphing what we just already previewed. So for you to be able to do this, you have to remember how to graph a line. Remember that when we graph lines, the easiest form to graph in is slope-intercept form. Y equals mx plus b. If your line, is already in that format, then graphing is a snap. You begin at the y-intercept, that's on the y-axis, that's at positive 5. You move with your slope. Remember, slope is rise over run. So if we're beginning at 5 and our slope is negative 2, we're actually going to travel down 2 and right 1 every time we go from a perfect point to the next perfect point on this line. You can keep going and draw an arrow at the end. You can reverse it. So the opposite of down and right would be up and left. So up, 2 left 1. And do your best to draw as straight as you can. Now, I am not great with, obviously, with graphing. So I'm going to do my absolute best to make it as straight as possible. It's not that bad. The points are the most important part because we want to see where those points intersect. So there's our red graph. Now, our blue graph. This is wonderful, but it's not in slope-intercept form. So for it to be graphed easily by hand, let's convert it. Remember that converting it just means solving for y, getting y by itself. So we're going to start by moving the x away by subtracting it. So negative 2y equals negative x plus 10. You might be wondering why I have negative x plus 10 instead of 10 minus x. It doesn't actually matter. Either one is fine. But I like this format because it models mx plus b a little bit more closely. Either way, it doesn't really matter. Now, I'm going to have to divide by negative 2 to get y by itself. And that means I divide everything by negative 2. So both of those components get divided by negative 2. So in the beginning, you've got negative x. Well, that's negative 1x. Negative 1 divided by negative 2 is positive 1/2. A negative over negative is a positive, and 1 divided by 2 is just 1/2. So we've got negative x over negative 2, is 1/2 x. 10, positive 10, divided by negative 2 is negative 5. So we have a minus 5. Now, if this is finally modeling mx plus b, we're going to begin at negative 5. The y-intercept is negative 5, so negative 5 on the y. And our slope tells us we're going to move, rise over run, up 1 over 2. So I go up 1, right 2, up 1, right 2. Oh, look at that. I'm going to keep it going. I'm going to go down 1, back 2 just to keep it and see the bigger picture. And then I'm going to draw my line. So the point was finding the answer, the solution. The solution is the point of intersection. What is the solution? What is the ordered pair? The point of intersection for our system. That would be the ordered pair 4, negative 3. Now, it's more than just the point where the two lines cross, where the two graphs intersect. It's actually the only x and y where if you plug in both of the x's into the equations and both of the y's into the equations, they will give you two true statements. So if you really wanted to check your answers, you could take x is 4 and y is negative 3, plug them in appropriately in these spots, and they would give you two equations that make sense, that give you a true statement. So here we go, substitution. Now, we've just graphed by substitution. You did that in Algebra 1, so I was going to do one quick example, and now we're going to move past it. Also in Algebra 1, you did substitution. It's a different method. It's an algebraic method. Instead of graphing, you can do this by doing some simple algebraic manipulations. How do we do that? Well, here we go. New example, new question. Let's do it. Step 1, pick a variable to solve for, and then solve for it. This can be any of the 4 variables you see. So when you look at this, pick what's easiest. When I look at the top equation, 3x minus 4y equals negative 5, and the bottom equation, negative x plus 3y equals negative 5, one variable in particular looks a little bit easier, in my opinion, to get by itself. And in my opinion, that is that x. The bottom x in the second equation doesn't have a coefficient other than a negative invisible 1. Knowing how we have to get our variables by themselves by reversing PEMDAS, by SAD mapping, we might have to really be careful and think through this, because if we have a number, a coefficient in front of a variable like the 3, eventually we're going to have to divide by that number if we're solving for that specific variable. So you want to do whatever looks easiest. In my opinion, a negative invisible 1 looks a little bit easier to get rid of than a 3 or a 4. So let's do it. Step 1, pick a variable to solve for, and then solve for it. So I'm going to take negative x plus 3y equals negative 5. And I'm going to solve for it. So I'm going to have to move the 3y and update my problem. Negative x equals negative 3y minus 5. Again, this is no different than negative 5 minus 3y. I'm just wanting to keep it with the variable first because I'm particular. And then, of course, to get rid of a negative, you simply divide by a negative 1 because that is a negative 1. So we're going to divide everything by negative 1, which is a fancy way to say switch the signs. Negative 3y divided by negative 1 is positive 3y. Negative 5 divided by negative 1 is positive 5. So we picked a variable. We chose the bottom x because it looked the easiest to get by itself. And then we got it by itself. We solved for it. So here comes step 2. Sub it in for that variable, but in the other equation. Sub it in the other equation. Well, let's talk about the other equation. The equation we didn't use is 3x minus 4y equals negative 5. So if we're subbing it into that equation, where are we going to put it? Well, this says x. So when I see an x, I'm going to put 3y plus 5 in its place. I see 3x minus 4y equals negative 5. So here we go. Instead of x, I'm going to put what x equals, which is 3y plus 5. Now, we're going to have to solve and then find the other variable. So you're going to do a little bit of algebra here, but it's actually kind of fun, at least in my opinion. Your natural instincts, your algebraic instincts are probably kicking in right now because more than likely you really want to distribute that 3. That's a great place to start. So sometimes you have to simplify before you can truly solve. So we have to distribute the 3, making 9y plus 15, and then keep solving. Keep simplifying. 9y minus 4y combine together to be 5y. So the left side of our equation is 5y plus 15 equals negative 5. The right side is negative 5. We will then subtract 15 and solve by dividing by 5. So if we subtract 15, negative 5 minus 15 is negative 20. Divide by 5. We now know that y equals negative 4. This is fantastic, but this is only half of the answer. Because remember, your answer is an ordered pair. So you just found the y coordinate of the ordered pair. So if my answer is the point of intersection, the POI, and that is an x and a y, you just found out that the y is negative 4. Make sure you put it in the correct spot. That's the y, so put it in the second part of the ordered pair. It happens all the time. Watch out for that mistake. Don't actually accidentally put that in the wrong spot. So how do we find it? How do we find the other one? Well, thankfully, we have an equation that's ready to go that tells us what x equals. X equals 3y plus 5. So if you take the fact that y equals negative 4 and you sub in that negative 4 for y, the rest is straightforward and simple. 3 times negative 4 is negative 12. And negative 12 plus 5 is negative 7. So your equation is solved, and your point of intersection, your solution to the system, is the ordered pair -7, -4. X equals -7, y equals -4. That was substitution. You literally manipulate the equations to where you get one variable solved for and you plug it into the other. The goal of that is that what you've done is you've taken the other equation and you have completely turned it into a one variable equation. You can't solve if you have x and y. You can solve if you have only y's or only x's. So that is the purpose of substitution. Now, the other algebraic method that we're going to talk about is elimination. Elimination is an interesting method that I think is actually pretty neat. It's actually kind of like old school addition. So here's what you're looking for. You're looking for a variable to eliminate. Similar to how we just plugged in one variable for the other and manipulated the equation into just one variable so we could solve using substitution. Well, elimination, you're again getting your equation to only have one variable. The difference is instead of putting one in the other, you're making one completely disappear. So the question is, what do you need to do to manipulate one or both equations to get one of the variables to disappear, like completely vanish? Notice that you can multiply one or both equations, and you can even multiply an equation by a negative. It's up to you figuring out what you want to do and how you want to do it. So let's talk about that. We have two options. We could eliminate the x's or we could eliminate the y's. In this example, if you choose the x's, you would only have to multiply the bottom equation by -2. The reason? Because the top equation of 10x minus 2y equals 16 has no reason to change. By multiplying the bottom equation by -2, that 5x turns into a -10x. And then, of course, we have to still keep everything balanced by distributing the -2 through. Notice what happens. The second step is treat it like old school addition and solve. Old school addition, like the big bar, big plus sign, how it's totally lined up in rows and columns. Look what happens. The x's completely eliminate. That's the job. That's what you want them to do. And now -2y plus -6y is -8y. And 16 plus 24 is 40. Now you have an equation that's solvable. You can divide by -8 in this case, and boom, y equals -5. Again, you already have half of your answer because your point of intersection is an ordered pair. You just happen to find the y first. There it is. Now, you will still have to go back and get the x. So you could obviously eliminate the y's this time and redo the whole problem, which seems a little silly. It would also take you a little bit extra work. If you chose to eliminate the y's, you'd have to multiply both equations. The top equation would have to get multiplied by 3 because that would turn the y into -6y. The bottom equation would have to get multiplied by +2 because then you'd have +6y and boom, they'd eliminate. So this is what I mean by sometimes you have to multiply both equations by whatever it takes to get a variable to have the same number but different signs so they zero out, so they eliminate. So you could do that, and that's fine, but that is a lot of extra work. It doesn't seem reasonable to me. So instead of doing that, why don't you recognize that you could simply plug in to any of the equations we've already used and then just solve for x. So you can plug into your original top equation. You can plug into your original bottom equation, You can even plug into the one you manipulated and it still should work out just fine. The question is, what looks easiest to do? Well, I kind of like the numbers on the bottom a little bit better, though it doesn't really matter. I'm going to go with those. So if I write that out, we have 5x plus 3y equals negative 12. And we already found out that y is negative 5. So if I simplify it, 3 times negative 5 is negative 15. And now all I have left to do is SADMAP it, is solve it. So I'm going to add 15. Five x equals positive 3. And I'm going to divide by 5. So x is a positive 3/5. So there's my point of intersection. There's the solution to this system. If you had chosen to put that negative 5 in the other equation, the only thing that would have happened is you would have had a fraction you would have had to simplify. It still would have been equivalent to 3/5. It's all the same stuff. As long as you do your math right, your simple skills right, you're not going to mess this up. You got this. So, last thing. Now, all of this, by the way, remember, has been a review from Algebra 1. It is totally okay if you don't really quite remember. It's been a while since you've seen it. That's why we're doing this video. That's why we're doing this extra section of, hey, let's just refresh some basics before we kind of Algebra 2-ify it. So, last part. What happens if we lose both of our variables? I want to remind you of the big picture here. At the beginning of this lesson, we talked about how there are 3 options. And so far, 3 options, like 3 types of solutions. One solution, infinitely many solutions, or no solution. Well, yes, there's 3 types of doing it, right? 3 types of solutions you're going to get, but there's 3 ways of finding them. So we've got 3 solutions and 3 ways to find them. We just did graphing, substitution, and elimination, and all 3 of those methods found this one. Found when we had one solution. Found when we had an actual point of intersection. So the question is, all right, that's great. How do you then figure out if you have infinitely many or no solution? So that leads us to here. It's what happens when you lose both of your variables. Now, if you find out and you're doing your manipulations and you end up losing both of your variables, do not panic. Do not paralyze in fear. You got to know it's okay to lose your variables completely. Just ask yourself if what's left over is true or false. If you end up with a true statement, no variables, but a true statement, something like 0 equals 0 or 4 equals 4, if those are true, then we say that there are infinitely many solutions. When the same graph is graphed twice on itself, 2 different equations giving you the same graph. If you end up having a false statement, like 0 equals 10, or negative 7 equals 107, those are not correct. Those are false. False answers, false statements, yield no solution. So here's a hint. One of these is going to be false and one of these is going to be true. We're going to practice our 2 skills, our algebraic skills. It's pretty easy to spot whether or not you have infinitely many because it graphs is the same line on top of each other, or if you have 2 graphs that don't touch, aka parallel lines, that then would have no solution. So I'm not going to worry about doing the graphical version of how to find infinitely many or no solution. So let's talk algebraic, and let's do it in the same way that we just did these other examples. Let's do substitution and elimination and have that skill reiterated one more time. So let's do this. The first one looks up pretty well set up for substitution. The second one we're going to do with elimination. Now, how did I know the first one was set up really, really well for substitution? Honestly, it's both. You could do elimination or substitution here, The reason why I'm choosing substitution is because I found very quickly, or spotted really, that there was a variable that was super closely, almost, just maybe, super easy to do, almost by itself. So if I take that approach, just so we can have the extra practice, substitution was you pick a variable of the 4 you have to choose from, and you get it by itself. You solve for y in this case. So if I take 2x and I add it to the other side, I end up very quickly in slope-intercept form. Y equals 2x minus 5, or negative 5 plus 2x, same thing. So that was step 1 of substitution. What is step 2? You sub it in the other equation. So my other equation is 6x minus 3y equals 15. And since this is what y equals, when I see that y, I'm putting 2x minus 5 in its place. So 6x minus 3y is 15. And instead of y, I put what y equals, 2x minus 5. Now, if you're following along, and you know that we have to simplify before we can solve, your instincts kick in, and you know you have to distribute that negative 3. Well, negative 3 times 2x is a negative 6x, so I put a minus 6x. A negative 3 times a negative 5 is a positive 15, so I put a positive 15. When I continue simplifying, I notice that my 6x minus 6x are going to zero out. Oh no, I've lost my variables. I've lost both of my variables. There's nothing left. Do I A, panic? No. Do I B, paralyze in fear? No. Always C. Not always, but in this case, C. Remember that it's okay to lose your variables. Simply answer if the statement you have left is true or false. And if it's true, it's infinitely many solutions. If it's false, it's no solution. Well, 15 equals 15 is very much true. So we actually have infinitely many solutions. Every point on that line is going to intersect with every point on the other line. So we have 2 lines that end up graphing on top of each other, touch everywhere. Therefore, we have infinitely many solutions, and that's too many to name. So we just stop. Okay, let's do the last example. Elimination. Elimination, the one we just did, was picking a variable and deciding to, if you have to manipulate it, multiply it by something, or, give it a negative, whatever you need to do to manipulate it to make a variable eliminate. So your first step is, what do we want to eliminate? Let's see, we eliminated, what over here? Eliminate x's on the first one. So let's eliminate y's this time. It doesn't really matter. You do what you gotta do. Whatever looks easiest for you is fine. So if we choose to eliminate y, that means that I need to focus and figure out how to turn a 4y and an 8y into the same number but opposite signs. Well, if I multiply the top equation by negative 2, I'm going to distribute that through, we have negative 6x minus 8y equals negative 36. The bottom equation didn't need to change because we had a positive 8y, and that was my goal. My goal was to get the y's to eliminate, and multiplying by the top by negative 2 totally did that. It made negative 8y when the other one was positive 8y, so it zeroes out. So we treat it like old school addition, but oh no, watch what happens. When we distributed the negative 2, it changed the other 2 values, the variable and the constant. And that became a negative 6x minus 8y equals negative 36. If I add my x's together, they zero out. They're gone. If I add my y's together, they zero out. They're gone. I literally have nothing, goose egg, 0 values on the left of that equal sign. On the right-hand side, I have negative 36 plus 18. Well, that is negative 18. Oh no, I've lost both of my variables. Do I panic? No. Do I paralyze in fear? No. Remember, it's okay to lose your variables. Just ask, is what you have left true or false? 0 definitely does not equal negative 18. That is a false statement. And false statements, we must then conclude, mean that there is no solution. So if I graph these two equations, these would end up being parallel lines that don't touch ever. Hence no intersection, hence no solution. Okay, that's it. This has been a crash course in Algebra 1. Thank you for sticking with me to the end. In our next lesson, we are going to take what we just did right now with substitution, elimination, and graphing. And this time we're going to branch it out and we're going to apply it to lines with parabolas and even parabolas with parabolas. Stay tuned.